Hello and welcome to another lecture for Introduction to Astronomy. Today's topics are the moons of the outer solar system, the rings of the planets in the outer solar system, the debris such as asteroids and other bits of rocks that are out there, and also we'll talk a little bit about Pluto. So today we will learn about the different types of asteroids that are in our solar system, as well as the largest one, Ceres. We will learn how planetary rings formed around the giant planets and a little bit about how they evolve over time. We'll also discuss the Galilean moons in more detail. We are familiar with them from our history of astronomy with our discussions of Galileo. We'll also discuss the characteristic of Saturn and Neptune's largest moons, those being Titan and Triton, respectively. We'll also discuss the discovery of Pluto and the other dwarf planets that are in our solar system. And lastly, we will talk about comets and where they come from. So far in our journey through the solar system, we've been looking at the planets and the terrestrial planets and the gas giant planets, the Jovians, but there are also a lot of other smaller objects in our solar system that we can study. And so many of these other objects exist out beyond the orbits of Mars, and they are very unique celestial bodies that are all gravitationally bound that have their own unique sizes, dynamics, and potential origins. And we'll be studying them using our comparative planetology methods that we've been using before. So many of these objects that we know of are in the asteroid belt. These are our asteroids that are in between the orbits of Mars and Jupiter. But there are a few asteroids that are on the interior of Mars's orbit, so that is, they're closer into the sun. But the vast majority of the asteroids are in the asteroid belt, and there are actually a few that are in the same orbital path as Jupiter that follow in front of and behind Jupiter in its orbit. So there are asteroids all over our solar system, not just in the asteroid belt. So asteroids were first discovered in 1801 by Giovanni Piazzi. And these are rocky bodies that have a large tendency to be in big clusters, with the vast majority of asteroids found in the asteroid belt, that region between Mars and Jupiter. And so there are actually three main types of asteroids. We have the C type, which stands for carbonaceous asteroids, which are dark, primitive bodies of rocks, of silicates and other organic compounds. We also have the S type for the stony asteroids, which are composed primarily of silicates, and they are presumed to have formed in a different region of our solar system than the carbonaceous ones. And then lastly, we have the M types, the metallic asteroids, which are composed primarily of metals, and these show signs of having very early heating and that differentiation that we know of from our planetary formation. The largest asteroid is Ceres, which was actually reclassified as a dwarf planet in 2006. It is technically a C-type asteroid that shows signs of being partially differentiated, and it even has evidence potentially of a subsurface ocean. So Ceres is a very interesting body, and we can see in the diagram on the left that it is located in the asteroid belt in between Mars and Jupiter. Next, we move on to discussing the rings of these giant planets. So each giant planet has a series of planetary rings, and these rings are composed of what we call little moonlets. These are tiny little rocks. They can be anywhere from pebble sized up to little boulders, but they have a wide continuum of sizes and they make up the ring systems. So Saturn's ring system is composed primarily of icy reflective particles, and they have a vast range of sizes, and they are very, very visually appealing. I would say that Saturn's by far the prettiest object in our solar system just because of those rings. That's just my opinion. You may have a different one, and if you do, we could have a little discussion in the discussion board about our favorite objects in the solar system or our favorite objects in space. I think that'd be pretty fun. Back to the lecture, though. So we've got Uranus and Neptune, and they have very dark, nearly invisible rings that are made of carbon and other hydrocarbon compounds. But the most elusive rings of all are Jupiter's rings. They are very, very faint and very small, and there's not much left of them, which kind of suggests that ring systems are temporary structures that are evolving over time. So understanding rings is still a work in progress. And so astronomers have postulated two possible origins for how rings are formed. There's the breakout hypothesis, which suggests that rings are the remains of shattered moons. And there's also the makeup hypothesis, which suggests that rings are leftover formation material that were unable to form into moons. So, which one is correct? Well, astronomers are still trying to work that out. So, I talked a bit about how these rings are changing and evolving over time, and one of the main ways that rings change is through this process of resonance. So, it's a little complicated, but I'm going to explain it in some simple terms so that we can understand it. So, as these individual particles of the ring orbit around the planet that has individual moons, it is going to experience gravitational pulls that perturb its orbit due to the presence of these large moons as they go through their orbit. So sometimes it's going to be pulled into different parts of its orbit as the moon aligns with the planet or as the moon is in a different position in its orbit. So when a moonlet and a nearby moon have orbital periods in exact ratios to each other, that is one orbit for the moonlet and two orbits for the moon, or vice versa, they have resonance in their gravitational pulls and the gravitational fields. And so at repeated locations along the moonlet's orbit, the moonlet is going to experience a maximal gravitational pull. And after so many oscillations, eventually the moonlet is going to have experienced so much of a pull that it now resides outside of the area where it can be in a stable orbit there in the ring. So this creates distinct gaps over time in these ring structures. So it may have started out smooth, but over time, these ring structures resonate and create bands in distinct locations that follow these mathematical ratios very precisely. Now let's talk about the outer solar system moons. So in the inner solar system, we don't really have many moons at all. We just have the moon, and then we have the two moons of Mars, Phobos and Deimos, which are very similar to captured asteroids. But in the outer solar system, we have 158 confirmed moons. Actually, in our total solar system, we have 158 confirmed moons. But there's only 3 in the inner solar system. So there's 155 out in the outer solar system orbiting the giant planets. And there's another 56 potential moons awaiting confirmation. And so each moon in the outer solar system is unique in its composition and its origin compared to the inner moons. The outer solar system moons formed in much more distant, colder regions because remember, we are many more AU out compared to the inner solar system once we reach Jupiter. And this results in icy, dark organic compounds on their surface, which are very unlike our own terrestrial moons. And along with their surface characteristics, the Jovian moons have very peculiar orbital transits. So nearly a third of the moons around Jupiter orbit in prograde direction along the equatorial plane. So they are orbiting with the direction of the equatorial plane. That's the pro in prograde. And 2/3 of them are orbiting in the opposite direction of the equatorial plane. So that is in retrograde. And this suggests that many of these moons may have not formed in conjunction with their Jovian planets, but instead were captured by the immense gravitational fields of these gas giants. So we can see on the image of in the diagram of the orbits of the moons around Jupiter, we can see that there are distinct groups. We can see that the Galilean moons are the Galilean moons are the innermost and they are prograde. And then there's another prograde group. And then a lot of the further outer moons of Jupiter are retrograde. So this suggests that they may have been captured instead of forming with the planet. But there is one moon out in the retrograde group, Valdudo, that actually orbits in prograde, despite being out in the retrograde group. So maybe that one formed with Jupiter instead of being captured. So there are quite a few large moons in the outer solar system. 79 moons are assumed to be orbiting Jupiter, and of those, the four largest are the Galilean moons, Ganymede, Callisto, Europa, and Io. Saturn, though, is assumed to have the most moons, with currently a confirmed total of a potential total of 82. 29 are still waiting to be confirmed. Saturn's largest moon, though, Titan, is very unique in the solar system and is the largest moon in the Saturn system, but it has a very thick atmosphere and it has liquid methane on its surface. It's a very interesting moon, that Titan. And then there's also Ganymede, which is the largest moon in the solar system, a little bit larger than Titan. But Ganymede is, again, one of the moons of Jupiter. Uranus has some very unusual moons due to the orientation of its axial tilt. It has 27 moons that are composed primarily of ice, and there could be even smaller moons yet to be discovered. And Neptune has about 14 moons, because there could be some more still to be discovered as well, because Neptune's very far out there. But the most exciting moon of Neptune is Triton, which is a retrograde moon and is presumed to have been somehow captured by Neptune's gravitational field. So the exact way that a moon could be captured by the gravity and enter these orbits are still not well understood. So we've talked about them quite a bit, so now let's get to know them up close, the Galilean moons. These are Ganymede, Callisto, Europa, and Io, and they were visited by the Galileo orbiter in the late 90s and extensively studied. So, Galileo found that the largest moon in our solar system, Ganymede, is nearly twice the mass of our moons and twice the mass of our own moon and half the diameter of Earth, suggesting it has a composition and a density that is unique compared to other terrestrial objects with a density of 1.9 grams per cubic centimeter. Ganymede is an icy world today, but it has evidence that shows it is differentiated. And surprisingly, it is not a dead world, but experiences intermittent geological activity because it has a relatively young surface, which is approximately 2 to 3 billion years old from those crater countings. However, the volcanism on Ganymede is episodic due to the immense gravitational field of Jupiter that Ganymede resides in. And there's other nearby large moons that pull on Ganymede's core, and so that gives it some tidal heating as its core is pulled in different directions from gravitational forces. The second largest Galilean moon and the third largest moon in our solar system is Callisto. So Callisto is 1.5 times the mass of our moon and has a diameter just smaller than Ganymede. Unlike Ganymede, Callisto never fully differentiated and froze before that process was done. And so this means Callisto is a geologically dead world. It is far less rocky and has an icy interior with a less dense core, giving it an overall density of 1.8 grams per cubic centimeter. And since it's geologically dead, its surface is a relic of 4 billion years of impacts, and it is the most cratered object in our solar system and the most cratered object known in general. And so it really gives us a really deep look into our solar system's chaotic past. But unlike many dead worlds, Callisto has a fun little secret. It was discovered in the late 90s that Callisto has a weak fluctuating magnetic field due to the large magnetosphere of Jupiter. And so this suggests that there could be a salty ocean underneath the surface of Callisto that carries charged ions, and that means that there could be a little bit of potential for life. The other Galilean moons, Europa and Io, are far rockier though. And so, despite a lot of infrared radiation, Europa retains much of the water on its surface under a thick layer of ice. And so, it's very likely that Europa is harboring a vast subsurface ocean and is often considered the only other large body with enough liquid water to be a likely place for life beyond Earth. And so Europa has a lot of unusual features on its surface, very thick, icy crevices and canyons on there. And so there's a mission heading there. Actually, I think currently on its way there. I think it's already launched. It's called Europa Clipper, and it is going to be an orbiter that is going to orbit around Europa and is going to study the surface and take a lot of infrared images and whatnot to study the potential dynamics of the crust and potential subsurface ocean. So it's not going to send anything down there and study it physically, but it's going to study it from orbit. So that's going to be very exciting. And the last Galilean moon that we have is Io. Io is the one in image 16. Europa is the one that's labeled image 15. So Io has a lot of volcanic activity on it, and it's very similar in size and composition to our moon, but that volcanic activity suggests that it has a very different history entirely. So it has the highest levels of volcanism in our entire solar system, with up to 50 eruptions a year, with over 100 recently active volcanoes. And this volcanism is due a lot in part to its interactions with Jupiter, and it's the immense gravity of Jupiter that causes it to experience the phenomenon that we call tidal heating inside of its interior. And so Jupiter's pull on Io, along with perturbations in Io's orbit due to pulls from Europa and Ganymede, have twisted that interior, and this fuels a lot of volcanism, which sends out a stream of charged particles into the atmosphere of Io and then out into the magnetosphere of Jupiter. And so Io is actually contributing to that magnetosphere by continually pumping out charged particles. So now we leave the Jupiter system behind and we arrive at Saturn to study its very interesting moon Titan. Titan is Saturn's largest moon and is the second largest moon in our solar system behind Ganymede, but larger than Callisto. And it was first discovered by Christian Huygens in 1655 and is very similar in size and density to Ganymede and Callisto. However, the big difference of Titan with Ganymede and Callisto is that Titan has a very thick atmosphere, which results in liquid precipitation, that is rain, of hydrocarbons, ethane and methane, despite having a very cold surface temperature. And that's because it's got this thick atmosphere. So the atmospheric pressure on the surface of Titan is 1.6 bar. For reference, our atmosphere is 1 bar, and so this is higher than any other known moon, and is composed primarily, its atmosphere is composed primarily of nitrogen. But it has actually a very complex atmosphere chemically due to the interactions of sunlight, which creates what we call a photochemical haze that is rich with organic molecules over Titan. So Titan is brimming with very complex chemistry. The Cassini orbiter was sent by NASA along with was sent out to the Saturn system, and it sent out the Huygens probe through Titan's atmosphere, and it successfully landed the Huygens probe on the surface, and this became the first spacecraft to land on the surface of a world in the outer solar system. The Huygens probe landed alongside a hydrocarbon lake, and it measured a lot of the surface environment for about an hour before it froze and no longer functioned. That's because it was minus 292 degrees Fahrenheit on the surface there. And this suggests, many suggest that the abundant hydrocarbons of these lakes near the poles are coupled with many suggest that the abundant hydrocarbons in these lakes, coupled with a lot of geologic activity and that interesting atmospheric composition, could result in some really interesting life developing potential on the surface. So we could have some very interesting chemistry potentially developing life on the surface of Titan. So it is definitely a place we want to send some more probes to study. So now we move on to Triton, which is the largest of Neptune's 14 moons and is the next major moon we're going to study. So Triton is a retrograde moon, and it is assumed to be composed of a 75 to 25% mixture of rock to ice. And it has some of the coldest surface temperatures of any object in our solar system, with a surface temperature of minus 388 degrees Fahrenheit, or we could say that is 40 degrees Kelvin. So many of the gaseous elements and compounds are frozen on Titan due to it being extremely cold. So the water, nitrogen, methane, and carbon monoxide are all frozen. But there is actually a small fraction of vaporized nitrogen that exists near the poles that is forming a very, very thin atmosphere. So there are actually some hazy clouds on the poles of Titan, or of Triton, We were just at Titan. We are now at Triton. Triton's rocky surface has some impact craters, but not that many. So this suggests that its surface is relatively young. But it's actually not. It wasn't covered by molten lava, but rather by water and ammonia mixtures, which give it a very unusual surface geography. Along with this weird surface geography are some nitrogen geysers in the southern polar area, which emit that nitrogen gas that give it that very thin atmosphere. And that is also most present during the seasonal periods of its axial tilt when it's nearest to the sun. So there are actually even seasons on the moons, which is pretty cool. So now we move on to talk about the tiny elephant in the room. That is everyone's beloved little planet, now a dwarf planet, Pluto. So Pluto has a very contentious time being widely considered a planet by many growing up, but now astronomers have reclassified Pluto as a dwarf planet. So let's get into the nitty-gritty of the history of Pluto and a bit about why it is now considered a dwarf planet. So, after the discovery of Neptune, there were still some small irregularities in the orbit of Uranus, so this suggested there was once again a planet X lurking out beyond the orbit of Neptune. Using the calculations from these irregularities, which are now considered to be inaccurate, this led to the accidental discovery in 1930 of a small rocky body that we now know as Pluto. Eventually, it was discovered that Pluto had another binary companion, a very large moon by the name of Charon, and that from these two masses, it was determined that that was not enough mass. It was far too small to perturb the orbit of Uranus, and so the planet X was then sort of written off, and Pluto was considered for a long time to be a planet. However, better observations and orbital calculations of Pluto and Charon suggested that they actually move like a binary pair, and they have four smaller moons that are orbiting around them that have not completely escaped yet. So it's kind of a potentially unstable system. And so that system is still evolving. And because of this, in 2006, Pluto was reclassified with many trans-Neptunian objects as a dwarf planet. So one of the main uh, things that defines a planet is that it has cleared its uh, neighborhood, so to speak. So it is the most dominant body in its orbit around the sun. So it's very clear for the Earth that the Earth is the dominant body of the Earth and the Moon system. Uh, Jupiter is the dominant body of its 60 plus moons that are orbiting around it. However, Pluto is not the dominant body of its system. Pluto and Charon are roughly the same size, and so rather than Charon orbiting around Pluto, they orbit around each other. And so it's not really clear what the largest thing, the most dominant gravitational body in that system is, and so it's not considered a planet for among many reasons, that being the primary one. And so Pluto being so far away, we didn't have a very good look at it until 2015 when the New Horizons probe went by, and that gave us a lot of surprises. It was long thought that Pluto would be geologically dead. However, Pluto's surface is actually very active in appearance. I say very active. This is relatively recently, so still millions to billions of years ago. But Pluto's surface had some dark red areas in lowlands, along with pale, smooth substructures, which suggests a lot of geologic activity in Pluto's history. So I mentioned in the last slide that Pluto was reclassified along with many other trans-Neptunian objects as a dwarf planet. So trans-Neptunian objects were once hypothesized little bodies out beyond the orbit of Neptune, which have now been discovered in a quite a large number. So on this graph, we can see a little bit of the density of these bodies out as we go further out in the solar system. And so we have a lot of very similar objects in size to Pluto that are out in the Kuiper Belt. And then even further out, we have some smaller objects. And then there's Eris, which is actually about the size of Pluto, that is much further out. So trans-Neptunian objects are small worlds that are outside the orbit of Neptune, and they are less influenced by the sun's gravitational field. We call the largest of these dwarf planets, and they have not completely escaped the immediate gravitational field of their neighbors, which is what I was discussing in the last slide about Pluto not having cleared its uh, nearby gravitational field. So there's still a lot of fighting to determine what's going on in these orbits. And that's because these are very far out orbits, and so it takes a long time for their interactions to eventually settle down. And there are only 5 universally accepted dwarf planets: Ceres, Pluto, Haumea, Makemake, and Eris. And the majority of them reside in the Kuiper Belt, which is just outside of Neptune's orbit and is similar in density to the asteroid belt, but with a lot more icy bodies. But not all of the trans-Neptunian objects stay out in the Kuiper belt. Some of them dive into the solar system because they are on very eccentric orbits. These are our comets. Comets are small chunks of icy material that develop a very faint nebulous tail as they approach the inner solar system, and they start melting, and that material is blown behind them due to the solar wind. So the earliest studies of these comets date back to Isaac Newton, who suggested that comets orbit the sun with a high eccentricity. And his then colleague, Edmund Halley, predicted the occurrence and calculated the orbit of 24 known comets, the most famous of which is Halley's Comet. Halley's Comet has been very well documented throughout history since 239 BC and is named in memory of Edmund Halley when it reappeared in the sky in 1758 after his death, and based on his calculation. And this continues occurring once every 78 years and will return again in 2061. It's a very dramatic comet. My parents always said that it was just incredible to see such a bright comet in the sky. I have yet to see a very bright comet in my lifetime. I've seen some through binoculars and with longer exposures with my camera, but I've never seen one that is just like naked eye, bam, there it is in the sky. That's clearly a comet. So I'm still waiting for that. Comets that return in measurable human time intervals are known as short period comets. But the majority of comets are long period comets, and that some of these can take thousands of years to return if they return at all. In the 1950s, the composition and dynamics of active comets were first proposed by Fred Whipple, and he suggested that comets generate a temporary atmosphere, which is called a coma, which is fueled by a small solid nucleus inside, and this coma quickly escapes into two tails, the dust tail and the ion tail. So these comets, the short period ones, originate as trans-Neptunian objects, and when they experience small gravitational pulls from giant planets along their orbits, they get pulled into the inner solar system and light up as comets. However, long period comets are unique. We hypothesize that these long period comets originate out in a region called the Oort cloud, which is named after Jan Oort, who first suggested that very far trans-Neptunian objects at the boundary of the sun's sphere of gravitational influence may be within the range of nearby passing stars' sphere of influence. So the Oort cloud is the very furthest reaches of our sun's sphere of influence. And so occasionally our sun's sphere of influence might bump into another sun's sphere of influence, which then perturbs these objects in the very outer parts of the solar system and occasionally causes them to accelerate into the inner solar system. So ultimately, these comets continue their highly eccentric orbits, sometimes unscathed until they pass near the sun, where they are either destroyed, can spontaneously break apart, or they become influenced by the gravity of another larger object and then move on to a different orbit than before. So comets are very cool objects. A lot of them are still being discovered because they have such long periods that astronomers haven't seen them head towards the inner part of the solar system yet. So very exciting times if we are waiting for comets because we never know when the next one will start potentially lighting up our sky. So it's very exciting. This concludes our lecture on the moons of the outer solar system, asteroids, comets, and all of the tiny little rocks that make up the outer solar system.